If you want to know exactly what kind of life can survive in a specific part of the world, you only need to look at two atmospheric forces, temperature and precipitation. These two variables define a biome. This is a climatogram. Scientists use it to chart invisible geographic boundaries. The baseline axes map average temperature and rainfall. By reading the intersection of these two datasets, we identify the exact ecosystem. High temperatures and sharp wet-dry contrasts point to a tropical savanna. This precise intersection of heat and moisture sets strict biological limits. It determines whether a landscape can support a dense canopy of towering trees or if it will only yield sparse, drought-resistant shrubs. The Earth's surface is not a random assortment of habitats. It operates as a highly ordered grid where the atmosphere chemically constrains exactly where life can take root. Near the equator, we find the tropical rainforest. This biome possesses the most stable temperature and moisture profile on the planet, averaging between 68 and 93 degrees Fahrenheit year-round, with frequent, intense rain. Because there is almost no temperature seasonality, plants do not experience dormant periods. This continuous, year-round primary productivity fuels massive biodiversity. With water and warmth in constant supply, the limiting factor becomes sunlight. The intense competition for light forces the forest to scale upwards, intercepting so much radiation that just 2% reaches the sparse forest floor. Plants adapt to this severe light scarcity near the ground through epiphytism. Instead of rooting in the nutrient-poor soil, epiphytes grow entirely on the trunks and branches of other trees, catching moisture and sunlight high above the dirt. In a perfectly stable biome, life builds upon itself vertically. It creates dense, overlapping microhabitats that rely entirely on the structural architecture of the canopy to survive. Contrast that equatorial stability with the desert biome. Here, extreme heat and lethal water scarcity replace abundance, creating an environment that routinely kills unadapted species. To survive these conditions, desert mammals have evolved highly specific survival strategies. Scientists classify these mammals into 3 genomic categories based on how they handle heat: evaders, endurers, and evaporators. Evaders, like small rodents, avoid extreme temperatures behaviorally by hiding in burrows during the day. Physically, they minimize water loss by excreting highly hyperosmotic, concentrated urine. Endurers, on the other hand, are large ungulates like camels that cannot easily hide from the sun. They rely on localized fat storage and extreme internal temperature tolerance, metabolizing that fat into highly efficient, usable water to survive without shelter. When macroclimates are pushed to their absolute limits, long-term survival requires slow, generational, and highly rigid genetic adaptations. We see this same evolutionary rigidity underwater. Coral reefs are a fragile marine biome defined by a strict upper limit threshold of ocean water temperature. The foundation of a reef is a microscopic symbiotic relationship. The coral animals provide shelter, while their algal partners, called zooxanthellae, produce food through photosynthesis. This animated chart illustrates 2026 climate data on ocean acidification. It maps the direct inverse relationship between rising atmospheric carbon dioxide levels and plunging ocean pH. This reduced carbonate availability severely interferes with the coral's ability to calcify and build their rigid shelters. Combine this acidity with sudden spikes in water warmth, and the stressed coral are forced to expel their symbiotic algae. The reef loses its color and its primary food source, resulting in mass bleaching and starvation. These highly specialized microadaptations took millions of years to form. When human-driven temperature shifts happen in a matter of decades, they trigger systemic ecosystem collapse well before evolution has time to respond. Global warming is now physically migrating the boundaries of life. Look at the boreal forest, the world's largest terrestrial biome, which is currently warming faster than any other forest type on Earth. NASA Landsat data proves that over the past 4 decades, this massive biome has grown by 12% and physically migrated northward by nearly 1/3 of a degree in latitude. As the forest advances, the Arctic tundra retreats. The rising temperatures that allow the trees to move north are simultaneously rapidly thawing the permafrost, the permanently frozen layer of ground that lies directly beneath the tundra. The physical manifestation of this thaw is violently visible. Stadium-sized retrogressive thaw slumps, massive mud landslides, are tearing the landscape open as the ice holding the ground together melts. This exposes a massive chemical threat. An estimated 1,400 gigatons of carbon, 4 times more than humans have emitted since the Industrial Revolution, have been historically trapped in this frozen ground and are now poised to be released into the atmosphere. Climate change is physically uprooting ancient geographic boundaries. It is transforming the world's most critical carbon sinks into massive active carbon emitters. Because of this impact, conventional ecosystem maps are no longer accurate. Scientists have introduced a new classification, anthromes, or anthropogenic biomes, to describe the terrestrial biosphere in its contemporary human-altered form. In the 1700s, before the Industrial Revolution, most of the Earth's ice-free land consisted of wildlands. Today, the data shows that over half of that land has been transformed by agriculture and human settlement. Biological patterns are no longer solely dictated by temperature and rain. Sustained, direct human interaction with ecosystems is now the primary force shaping what grows where. We now categorize the Earth using intensive land use groups. Natural wetlands and vast grasslands have been replaced by constructed artificial wetlands, massive monoculture croplands, and dense urban settlements. Humanity has transitioned from a species existing within biomes to a global geologic force. We are actively overriding the planet's ecological operating system.